For nearly a century, scientists have struggled to explain a fundamental cosmic problem. Galaxies and galaxy clusters don't behave the way we expect. Stars in the outer regions of galaxies move too fast, and galaxy clusters appear to have far more gravity than their visible mass accounts for. To explain this, physicists proposed dark matter, an invisible substance that makes up 85% of the universe's matter, yet has never been directly observed. The idea is that dark matter only interacts through gravity. It doesn't emit, reflect, or absorb light, making it practically invisible. Decades of searching, billions spent, and still no direct detection. So we have to ask, are we missing something? And if so, what? To answer this, scientists have launched some of the most ambitious experiments in history to detect dark matter. But every time, the results leave us with more questions than answers. Either one, dark matter is real, and we just haven't found the right way to detect it yet. Or two, dark matter doesn't exist, and we're looking in the wrong place. But what if the answer isn't about what's missing, but about what's already there? That's why some scientists are asking, could plasma and electromagnetism be responsible for the missing mass? To find out, we'll explore why dark matter was proposed in the first place, how plasma behaves in space. We'll look at electromagnetism versus gravity, and ultimately what this means for the future of astrophysics. And it's important that when we challenge the mainstream narrative, that we use mainstream sources. And before we dive into the evidence, let's take a moment to define what real science is, and why questioning the mainstream model is part of the scientific process. Science isn't about clinging to a favorite model, it's about questioning everything and following the best available evidence. After watching, I encourage you to dig into the research for yourself. Before we explore alternative explanations, we need to understand why scientists even believe in dark matter. What were they seeing that couldn't be explained? And could they have misinterpreted the evidence? It begins in a distant galaxy cluster, the Coma Cluster, which is sprawling across the cosmos 300 million light-years away. In the 1930s, Swiss astronomer Fritz Zwicky set out to measure how these galaxies moved relative to one another. Using the Virial theorem, which links a system's kinetic energy to its gravitational potential energy, he calculated how much mass the cluster should have to keep the galaxies gravitationally bound together. Upon further study, a problem presented itself. The galaxies were moving far too fast, so fast that the cluster should have been torn apart, but it wasn't. Based on the visible matter alone, there wasn't enough gravity to keep the cluster intact. As a result, Zwicky proposed the idea of Dunkel materia, which later became known as dark matter, the proposed invisible mass that must be providing the missing gravity. At the time, his idea was dismissed because most scientists assumed he had made an error or that the mass was simply hidden in dim stars or gas clouds. Ultimately, Zwicky's discovery laid the first foundation for the idea of dark matter, even though it took decades before it was taken seriously. Fast forward to the 1970s, Vera Rubin and her colleague Kent Ford were studying how spiral galaxies rotate. In our solar system, planets orbit slower the farther they are away from the sun, since gravity weakens with distance. Rubin expected to find the same pattern in galaxies. Outer stars should move slower than inner stars. The problem was, that's not what she found. The outer stars weren't slowing down at all. Instead, they were moving just as fast as the inner stars, defying Newtonian physics. If gravity was the only force at play, the outer stars should have been flung deep into space. Ultimately, Rubin's data confirmed Zwickie's earlier suspicions. There had to be far more mass than what was visible. This resurrected the dark matter hypothesis, but this time scientists took it seriously. Her research forced cosmologists to consider the possibility that 85% of the universe's mass was invisible. The third clue came in the 1990s. If dark matter was real, then it should bend light the way regular mass does. Einstein's general relativity predicted that massive objects curve space-time, causing light to bend around them, a phenomenon known as gravitational lensing. In the 1900s, scientists began using advanced telescopes to study lensing effects in galaxy clusters. The problem was, the lensing effects were much stronger than what visible matter alone could explain. Some massive objects were bending light as if they contained much more mass than we could see. Scientists interpreted this as more evidence of dark matter. With the discoveries from Zwicky, Rubin, and lensing studies, dark matter became the default explanation for missing mass in the universe. It became a key pillar of the lambda cold dark matter model, which describes the universe's evolution. In this model, dark matter accounts for approximately 85% of all matter, while only 15% is ordinary matter, including stars, planets, and gas. However, when considering the total mass energy density of the universe, ordinary matter makes up just 4.9%, with dark matter at 26.5%, and dark energy dominating at 68.5%. The logic was simple. If we can't see the mass, but we can see its gravitational effect, it must be there. This was considered the strongest indirect evidence for dark matter. Today, gravitational lensing remains one of the primary arguments in favor of dark matter. The problem with this model is despite decades of searching, dark matter has never been directly detected. We only have indirect evidence in the form of galactic rotation curves, cluster motions, and gravitational lensing. Billions of dollars have been spent on dark matter detection experiments, such as the Large Underground Xenon Experiment, the Xeno N1T detector, and the Large Hadron Collider. After all of this, no conclusive evidence of dark matter has been found, and the question still remains, are we really seeing dark matter's effects, or have we misinterpreted the data? If we can't detect dark matter directly, maybe that is because it's not actually there. Could another force be responsible for the effects we see? What if plasma and electromagnetic forces are the missing link? Plasma already makes up 99% of the visible universe, yet it is rarely considered in these models. Unlike neutral matter, plasma interacts with electric and magnetic fields. If plasma structures are shaping cosmic motion, could we be misattributing their effects to dark matter? If plasma plays such a massive role in the universe, why is it rarely considered in dark matter models? Before we explore whether plasma could explain these anomalies, we first need to understand how it behaves in space and why mainstream cosmology tends to ignore it. Since Newton and Einstein, astrophysics has been dominated by gravity-based models, and many in cosmology assume space is electrically neutral, leading them to downplay plasma's large-scale electromagnetic forces. However, space is filled with charged particles that generate electric and magnetic fields, which can significantly influence cosmic structure. And perhaps most importantly, dark matter is mathematically simple, an invisible mass that interacts only through gravity. Plasma, on the other hand, is highly dynamic, reacting to electric currents, magnetic fields, and turbulence, making it far more complex to model on cosmic scales. Has plasma's complexity led us to overlook its influence on the very structure of the universe? Let's try to unravel some of this complexity. As previously mentioned, plasma isn't just another state of matter. It's the dominant state of matter in the universe. Plasma consists of charged particles, such as positive ions and free electrons, meaning it strongly interacts with electric and magnetic fields. Unlike neutral gases, plasma forms complex structures influenced by electromagnetic forces. Plasma is found in stars, nebula, interstellar space, and even within galaxy clusters. One of the most striking examples of plasma's large-scale behavior is Birkeland currents, vast electrical currents that stretch across the cosmos, resembling cosmic power lines that align with galaxy clusters and intergalactic filaments. It was first discovered in Earth's magnetosphere and later observed in deep space. These currents transport energy and charged particles, influencing the movements of cosmic matter. Some researchers propose that the forces within these currents contribute to galactic stability, reducing the need for unseen gravitational mass. But plasma's influence doesn't stop there. It also forms vast filaments stretching across intergalactic space. These plasma filaments act as a cosmic highway, connecting galaxy clusters and influencing mass distribution. These filaments align with the cosmic web, the large-scale structure of the universe. If plasma filaments guide the movement of galaxies, could they contribute to effects currently attributed to dark matter? While Birkeland currents and filaments organize plasma on cosmic scales, another crucial plasma structure, plasma double layers, plays a key role in regulating energy. Charge-separated regions in plasma act as natural capacitors, controlling electric fields and energy flow. In space, double layers have been observed in auroras, solar flares, and astrophysical plasmas. Some scientists suggest that if double layers exist on intergalactic scales, they could help regulate energy within galaxies, possibly influencing their stability without requiring dark matter. For decades, we've been told that gravity alone shapes galaxies and large-scale cosmic structures. But when we take a step back, a different picture begins to emerge. Mainstream cosmology has spent decades searching for an invisible mass to explain cosmic anomalies. But what if the missing mass isn't missing at all? What if the answer has been hiding in plain sight, woven into the very fabric of the universe itself? If plasma and electromagnetic forces can shape galaxies, could they also explain the very effects we attribute to dark matter? That's exactly what we'll explore next. As we've seen, plasma makes up the vast majority of the visible universe and interacts strongly with electromagnetic forces. But just how powerful are these forces compared to gravity? Electromagnetic forces are vastly stronger than gravity at the particle level, by a factor of 10 to the 39th power. Plasma interacts with magnetic fields, forming massive self-organizing structures that shape the cosmos. Despite being observed in galaxies, magnetic fields are rarely factored into traditional models. That's because many astrophysical models still prioritize gravity as the dominant force. overlooking the dynamic role of plasma and electromagnetism. Could plasma's ability to generate and sustain these fields be the missing factor in galactic rotation? To understand whether plasma's electromagnetic interactions can account for galactic stability, we need to examine how magnetic fields influence the motion of matter in galaxies. Observations show that magnetic fields play a far greater role in galactic structure than previously assumed. A study published in the Astrophysical Journal and archived in Harvard's ADS database examined the role of magnetic fields in the rotation of the galaxy NGC 6946. Researchers found that these fields significantly shape the galaxy's rotation curve, challenging the idea that dark matter alone is responsible. Here, scientists analyzed how magnetic fields influence the rotation of ionized gas in this spiral galaxy. To do this, they measured galactic magnetic fields and their alignment with rotational velocity. They found that magnetic fields affect how gas moves within galaxies, contributing to the rotation curve, a pattern typically attributed to dark matter. The alignment of magnetic fields and plasma flows suggest that electromagnetic forces play a stabilizing role in galactic structure. This means that galaxies may not require as much unseen mass as previously thought. If magnetic fields and plasma interactions contribute to galactic rotation curves, it challenges the assumption that gravity alone governs these dynamics. This finding raises an important question. Could plasma and magnetic fields replace dark matter? If plasma's interactions and electromagnetic forces can shape galaxies, why do we still assume dark matter is necessary? Some researchers argue that magnetic fields and plasma currents could stabilize galaxies without requiring missing mass. Others suggest that if dark matter does exist, it may behave more like plasma, interacting with electromagnetic forces rather than being purely gravitational. The idea that cosmic scale electromagnetic forces plays a significant role challenges decades of assumptions in astrophysics. If plasma and magnetic fields can shape galaxies, could they also explain the very effects we've attributed to dark matter? That's what we'll explore next. One scientist who's dared to challenge the dark matter model was Dr. Anthony Peratt, a plasma physicist who studied under Nobel laureate Hans Alfvén, the pioneer of modern magnetohydrodynamics. Peratt wasn't just a theorist. His background in electrical engineering and plasma physics led him to the Los Alamos National Laboratory, where he contributed to over 100 publications on plasma physics and astrophysics. While the rest of the scientific world was chasing an invisible particle, Peratt took a different approach. He looked at what we already knew about plasma, electric currents, and magnetism. Peratt's groundbreaking work centered on particle-in-cell, or PIC, simulations, a technique used to model the behavior of charged particles in plasma. He asked a simple question. If large-scale plasma currents exist in space, could they naturally form the structures we see in the universe? To find out, he fed the equations of electromagnetism into his computer models and let plasma evolve under its own forces. What emerged was astonishing. His simulations showed that when vast Birkeland currents interact over cosmic distances, they generate self-organizing magnetic fields. Over time, these fields sculpt plasma into structures nearly identical to spiral galaxies, with flat rotation curves, just like what astronomers observe. For decades, flat galaxy rotation curves have been cited as evidence for dark matter. But what if it's not missing mass at all? What if electromagnetic forces are shaping these galaxies instead? One of Peratt's most influential papers, Evolution of the Plasma Universe 2, The Formation of Systems of Galaxies, laid the groundwork for this hypothesis. This presents a huge challenge to the dark matter model. If plasma can generate self-sustaining structures that mimic the effects attributed to dark matter, then are we looking at the universe the wrong way? The dark matter hypothesis assumes gravity is the dominant force in structuring galaxies, but electromagnetic forces are 10 to the 39 times stronger than gravity at the atomic scale. If plasma dynamics are at play on cosmic scales, we may have massively underestimated their role in shaping the universe. Could this explain why dark matter has never been detected? If electromagnetic forces are strong enough to hold plasma together over galactic distances, could they be the real driving force of cosmic structure? We've spent billions of dollars searching for dark matter, yet plasma is everywhere, waiting to be explored. Maybe the key to the universe's greatest mystery isn't dark matter at all. Maybe it's the fourth state of matter, the state that makes up nearly everything we see. Maybe the answer was plasma all along. And if plasma can shape galaxies, influence cosmic structure, and mimic the effects we once attributed to dark matter, what else might it be capable of? Science isn't about clinging to old ideas. It's about following the best available evidence. If plasma's role has been underestimated, we may not just be refining our understanding of dark matter. We may be standing at the edge of a paradigm shift that redefines the very forces shaping the universe. Let me know what you think. It is your comments that help guide this journey and shape our community. And until next time, take care.